Okay, so recording in progress. Let me hide the floating meeting controls. So good morning and happy Wednesday. Thank you. I guess you all saw the message on the Slack channel. You might have colleagues that join later than now. And when they do, I'll certainly pause for a moment to inform them about the recording, which is just good practice. So good morning and happy Wednesday. Hopefully you all weren't impacted too much by the storm. Various communities throughout Worcester County were impacted very differently. So that being the case, today is more of a practical session, and we'll go over some of the usage of the things that we talked about on Monday's class. And right now, where I think we have 6 or maybe 7 weeks left in the semester. And so going from this point forward, we're going to pivot more to some of the analytical techniques. And the goal in another 2 weeks or so is to get you to the machine learning portion, the extraction of insights from the data. Okay, but before we begin, the usual administrative bits, the reading, I've extended 2 more days. Since we're still dealing with aspects of time series. And project number 3 is out. It is due a week from today, or was it yesterday? A week from yesterday, instead of a week from Monday, to account for my being late with it. There were some practical issues associated with the project, specifically getting data from trading economics. It has changed. Used to be able to scrape data from trading economics for free, minus certain levels of granularity and certain other details. But now to get the data that we need, it requires a subscription, which is $499 a month for the type of data that we need. So that being the case, I found another source for the Baltic Dry Goods Index data, that ticker. And it's not as good as from trading economics, but it'll do the trick for our purposes. And that being said, oftentimes for these sorts of problems, when you're dealing with data, you can either collect the data yourself, which is quite expensive and very labor intensive, but there are certain organizations like healthcare organizations and things like that that collect data themselves. But there are other domains where you're subscribing to data from various sources, and finance and market analysis is one of them. And these sources like Bloomberg, Trading Economics, and Reuters, they can be expensive for an individual, and their prices are usually tuned more to organizations and enterprises. So project number 3 is out, and it involves some experimentation where you're going to be making some decisions based on what you see in your analysis. And we're going to go over several aspects important to that today. Okay, any questions? How's everybody doing? Good. So I see there are 1, 2, 3, 4, 5 of you. Okay. All right. And remember, class participation is part of the grade. So I appreciate your live attendance. All right. So that being the case, where we last left off, some of the stuff we talked about, simple moving average. And we said with that, you're taking k many, depending on your window size, k many measurements in order. From the most recent date to the most current date, and you're taking an average, right? That's your average, your sample mean. And so it's called the rolling average because that window shifts forward in time. I'll direct your attention, let me select a color here, to this window in yellow. That's at the first time instant. And so here we take the first 5 measurements starting at the oldest time stamp associated with our data set. And at the next instant, this window, when we take the next measurement, see if I can steady my hand on the sketch pad, that window shifts 1 measurement later. And so the oldest measurement is rejected, and the next measurement here is accepted into that window, and you compute that average anew. And so mathematically, we have this expression. We have 5 consecutive measurements in sequence, xi through xi plus 4, and we just take the sample mean of that, the weighted average. And as such, you'll notice that each measurement has a scalar 1/5 associated with it, and you can think of this as a vote where you're voting to determine what the measurement should be. And so here we're taking a vote, so to speak, and each of the 5 consecutive measurements has equal say in what the value should be, which is one way to think of what the rolling average is. And so we talked about this idea of should each of the measurements have equal say, and sometimes you don't. Now, certainly when they have equal say, the utility of doing a rolling average is that it's a little bit more stable, because if you have some temporal sequence like we have depicted here on the blue curve, and you have a so-called window of measurements, 5 measurements wide, you're determining what the value should be for that instant in time based on a set of measurements. And so it's a little bit more stable, and it ends up smoothing out some of these jagged edges, these dramatic increases that you have in your graph, and these dramatic decreases that you might have. Now, for temporal sequences representing securities or stock on a short time horizon or short span of time, these things are going to change very frequently. And if you ever have access to a 15-minute delay that you might get through TD Ameritrade and other sort of personal brokerage accounts, you'll notice that it does change quite rapidly for various securities. Now, that being the case, if you want to examine the longer term direction, whether the security is increasing, decreasing, or remaining stable, these jagged edges are not very useful. And so this window rolling average is one way of so-called smoothing out these jagged edges, because the impact that it has on your jagged graph, I'll just kind of draw a jagged graph here, is to effectively smooth it out so that you're more able to see the trend, for example, this red curve, for that data. Because at the end of the day, for financial markets, what you're interested in is not the fine-grained behavior, but you're interested in the coarse or the gross level behavior for the price of a particular security, commodity, or bond. Any questions about this? And welcome to my basement workshop where I build lots of stuff. No questions? No? All right. And so one of the questions that we posed is, do you need all of the measurements in your window to have an equal say in what the value should be? And so sometimes, yes, you do when you want that smoothing and you want to see trend information, but sometimes you don't. And those instances, as we discussed, where you don't, are concerned when what's more important to you is the recent behavior of that time series. And so I'll direct your attention again to the graph that you see here. And suppose you were, for whatever reason, making trading decisions based on the behavior within a day and not within a week. And so if that's the case, if you had a span of 7 or 5 trading days, because there are 5 trading days, or 5 business days during a week, you might be more interested in the behavior for your security within, say, this region, more recent, the current day and 24 hours into the past. And so what this UMA, I don't want to pronounce it, I don't want to say the long version, what this exponential weighted moving average, or we've been calling UMA, does, it allows you to control how much of the value at each time step is dependent on the current measurement, x sub t, and on the historical measurements, this s sub t minus 1. And so with this UMA, you have control with this alpha, and we'll talk about it, about the incarnation of how you set alpha in the code. We'll comment on that. You can decide what percentage on a scale from 0 to 1 on the closed interval on the real number line, you can decide what percentage of what your understanding of the value is at each time instant, what percentage of it is influenced by the recency, the current measurement. And as we discussed, it's called exponential because of these terms. Here we have, when we iterate this recurrence relation, as we called it, we have a term here of a decimal, 1 minus alpha, times a decimal, 1 alpha, and then we have another decimal, 1 minus alpha quantity squared. When you multiply 2 decimals or more than 2 decimals together, that ends up getting smaller and smaller and smaller. And as we had discussed, if you were to plot out the natural numbers along the horizontal axis, 0, 1, 2, etc., and you have some number alpha, where alpha is between 0 and 1 on the real number line. And if you had alpha raised to the k power, where k are the natural numbers, you're going to get a curve that decays. And so here, the more terms, as you iterate your recurrence relation, you have more terms exponentiated to larger numbers, and therefore the end result is you're discounting or making smaller and smaller exponentially all of those terms in the past. And so the end result is that more recent observations count more, and observations that are further in the past within your window of observations count less in determining what that value should be at that time instant. Okay, any questions about this? No questions? Excuse me. Does that make sense? You still there?
Yeah, that makes sense.
Okay. So let's move on. And we had some examples in Python. We're going to spend most of our time in the Jupyter Notebook. And we showed the impact of different types of smoothing. We had the rolling average, and we had the UMA smoothing alongside the unmodified graph. And so we brought in the CSV file. In this particular example, it's Costco. And we computed those three versions, the unadulterated version of our time series, reported as the closing price column from our data frame. And then we have the rolling average of that same closing price. And then we have the UMA version. Now here in our API, and I'll bring up the website for the API here, and I misspoke last time, we have something called span. And so in the weird implementation of moving average, and Python isn't the only weighted moving average, exponential weighted moving average implementation out there, this span does not represent the window size. This span is used to calculate what alpha should be, right? And I'll show you that page. With UMA, because it's a recurrence relation, at least the implementation in Python, it's going to give you values for each calculated position at each time step for your consideration when you do UMA. And so you'll notice when you do an UMA smoothed window average, you're not really using a window. You're evaluating the first measurement, the second measurement, the third measurement, and for each one of them, you're getting a value. So you will not get not a number. What the span does, it allows you to set the alpha through a formula that I'll show you in the API documentation. You can also specify an option when you compute the UMA, alpha equals, and you give it some scalar value like 0.1. Right now, the 0.1 that I talked about is usually a default. That's a machine learning thing called a learning rate. And I was pretty sure, at least my experience with other libraries, that it was 0.1, but they have a really wonky implementation for how you set this alpha. And so in either case, for the rolling average, you have a window size, and that window size represents how many measurements over which you're computing this rolling average, and that window moves from one time instant to the next, as we saw in the previous slide. But for UMA, this span is not the same as a window. All it represents is indirectly how you set your alpha, and we'll have an example of that. Any questions about this? Does that make sense? Okay. So here in this graph, we showed the impact of the different types of smoothing. In the blue curve, we had the closing price for Costco in this example that was not smooth, and you can see a lot of variability. So we're going to have, if you were to visualize this distribution for closing price unmodified, you're going to have a higher variance and therefore a higher standard deviation. And as you all found with your discussion of the central tendency and for the standard deviation, if you have a lot of outliers or irregular measurements, the sample mean and the standard deviation are not robust measurements. And so you're more apt, or it's more stable rather, to use the median and the interquartile range. And so in addition to making it harder to see the trends, the unadulterated, non-smoothed closing price graph, the blue curve, is not going to give you as good behavior if you're trying to make your analyses. So that's why another reason why this smoothing is very important. And so here in the blue curve, you see a higher standard deviation. The graph is more, quote unquote, wiggly. Let's use that term. And then the red curve is the smooth rolling window average, where each one of the measurements in the window has equal vote. And then here, the green curve is the UMA version for whatever value for alpha results from a span of 10. I think it's 0.6 or something like that. So that being the case, even though smoothing is a good thing, it has an impact on your standard deviation for the distribution of your curve or the measurements from your curve in your data set. There are times when you want the more recent measurements to have a bigger impact on where the graph goes. And so that is why you might want to use the UMA version versus the rolling window average, the fair voting version of the curve smoothing. Okay, any questions about this? Excuse me. Still getting used to this live Zoom thing. It's been a while. Okay, does that make sense? Yes? Okay, all right, great. Thank you, Alexander. All right, so we also talked about this idea of leading indicators, and this was to give you a high-level background about why things like the Baltic Dry Goods Index is important, but also to explain to you about what leading indicators generally are. And so we said that cargo space, its price changes ahead of the market, and that can be commodities, it could be bonds, and it certainly includes securities. And so we talked about the global supply chain and how all of the waypoints, as they were, in the various stages of the development of a product or a food product or good, from the raw material on one side to the finished good on the other side of the supply chain, we connect them globally through a network of transportation modalities. And so the service modality cargo ship, we said, or service modalities in general, are cheaper than air freight because plane freight is a lot more expensive. And so we talked about cargo space being relatively stable. It wasn't easy. It's not easy to build a cargo ship. So you can't solve the problem of addressing expensive cargo space by just saying, let's build a few more ships. It doesn't happen that way. And so we use this to motivate the fact that cargo space is very stable, or at least the price for cargo space is very stable. It's not going to change very much because you can't disrupt the price by building more cargo ships. So that being the case, we looked at the Baltic Dry Goods Index. And so you can certainly plot the graph on trading economics. And as I alluded to before, if you were to download the type of data we need for Project 3, it'll cost you. And so we didn't want to do any of that for the assignment. So the substitution I've provided for in project number 3, it'll get you the data you need for the price itself, but it's not as good as what you get on trading economics. So with that Baltic Dry Goods Index, one of the questions that we're looking at is whether it leads Costco share price. And Costco is a big box membership-based retailer. And as such, they traffic in sales of a lot of goods, both dry goods, things like staples and other food items, as well as durable goods, things like electronics and household items like furniture and things like that. Okay, any questions? So the question that we have at hand is from data to actually calculate the lead time, how far ahead of Costco security does the Baltic Dry Good Index exist. And so how we're going to do that is by taking our version of our Costco data of a reporting period, and I think I have 1 year of reporting period represented, and then we also have the Baltic Dry Goods Index reported over the same period of time, and then I'm going to look at correlation between the Costco price and the baddie price, where I'm going to shift this baddie price using an API from the time APIs in Python. I'm going to shift it one measurement in time into the future, right? So I'm going to take a measurement and I'm going to take all the dates and then shift them one reporting period, and then 2 reporting periods, and then 3 reporting periods. So if the Baltic dry goods index is, say, 3 months ahead of Costco stock, then if I shift it 3 months into the future, then the correlation will peak at some point, and that's the measure of coupling in this example that I'm going to use. Does that make sense? Any questions? No? All right. So we had data for 1 year's worth of reporting from 2021 October to 2022. And so we downloaded this, we clean it, and we remove the blemishes. So we perform usual data cleaning, and that includes issues with the data as well as entries, making a decision about what you're going to do for entries that might be not a number. So then we're going to load it into data frame. We're going to compute different versions of the data over the reporting period, both the rolling average and the EMA version. Then we're going to find, and that's where we're going to spend most of the time, the lag that maximizes the correlation between that Costco security and the Baltic dry goods index. And then, of course, we're going to visualize it. All right. And then answer the question that we have at hand. Now, for project number 3, it's a little bit different. You're going to be downloading data for a number of securities representative of different areas of the market. And you're going to be answering a question concerning how COVID shutdown impacted those securities. All right. So in answering the question then, once we know the lag for the Baltic dry goods index that maximizes the correlation, we can plot both the regular version of Baltic dry goods as well as the lagged or shifted in time version of Baltic dry goods. And then with that visualization, you can actually see that when Baltic dry goods in the red goes down, the Costco stock also goes down. Okay. Any questions about this? Does that make sense? No questions? All right. So let's exit the PowerPoint. And let's bring up the Jupyter Notebook. And I don't see the share. So let me stop the share. And let me redo the share. And where's my Jupyter Notebook? Where is it? Let me see. That's my calendar. Firefox, it's in Firefox. So let me see if that one works. No, that's the browser. I need that one. Please bear with me a moment or two. Let me try that again. Jupyter Lab, here we go. That's what I wanted. Shift. Okay. So let's bring up the Jupyter Notebook. Can you all see the Jupyter Notebook? Can you see that?
Yep. Yeah.
Okay, great. Thank you. All right. So the first thing I'm going to do, I'm going to bring Firefox up. So here is the Pandas data frame EWM API documentation. And for this, you'll notice one of the options, you have alpha equals none here. And if you don't specify a value for alpha is a scalar between 0 and 1 on the closed interval on the real number line. If you don't specify an alpha, it's going to use the span to calculate alpha. Why they did it this way is very curious to me. It's very interesting. But I'm certain if you kind of post it on various forums where the implementers of Pandas live, you get an answer for that. But nonetheless, if you don't specify a value for alpha, but you have a span specified, alpha is going to be set to 2 divided by span plus 1. And the span has to be greater than 1. And so span is not a window width because this is a recurrence relation. It's going to calculate a value for every measurement until that weighted average, that weight goes to 0. Okay. If you do specify alpha, it's of course just going to ignore the span, and it's going to set alpha directly to that scalar that you specified. Any questions about this? That makes sense? Yeah. All right. So the window span does not really matter for EWM. It's a matter of setting your alpha, and you can do that two ways, by using the alpha option as well as by using span. Okay. So let's go to, let me minimize that doc, and let's go to maximize that. Let's go to the Jupyter Notebook. Let me move this. Okay, so here I'll start out. Let me switch to my mouse here. We'll start out by importing the libraries that we believe we need for this analysis. And then I have some global variables, and it's my style. You can adopt your own style, but it's my style to begin with the libraries I need, set all the global data structures and variables that I need, and then have the code that I need. And so I start out and I set the smoothing window size of 10 that I'm going to need later on when I compute the rolling average version of my time series. And then I also set my time steps. And this max time steps is what I'm going to use to calculate the lag. And so I have an upper bound on the number of time steps I'm going to assume that the Baltic Dry Goods Index leads or precedes each one of my securities. Now, it's up to you to set what something like this is, right? And that's part of your assignment. The theory says that the Baltic Dry Goods Index is about a 6-month leading indicator, plus or minus, depending on a number of things. So that being the case, I set my globals, and then I ingest the data set that I need. In this case, it's Costco.csv, which I will not provide to you. It's for part of your data wrangling to go off and get these data sets yourself. And so I ingest my data set, and it's very useful in the next frame. It's very useful to take a look at your data set. This does two things. It kind of ensures that you cleaned your data appropriately, and it also allows you to verify things such as replacing the default index in the data frame with the date field. And so here I've looked at the CSV file ahead of time, and I was told that to use the date column to replace the index. And so index column is equal to date, and you specify a key name. This is case sensitive. That's important to remember. It's case sensitive based on what's in your CSV file. And then I tell it to use my default parsing rule, which you can certainly specify to be different if you choose. And I'll defer or point you to the documentation, API documentation, for what your options are for parsing. Okay, any questions about this? Does that make sense? Okay. So I ingest my data, and I take a look at my data. Everything looks pretty good. And now I'm going to compute my rolling window average. And so here, my window size, I like to use globals. You can hard code it, but I'm a big fan of things that are adjustable in one place instead of 10 places in your data set. And so here, my window size is 10. And so I'm going to compute my rolling window average. So each of the 10 measurements in that window, sliding window, are going to get equal, say, 1/10 and what the value should be. So when I take a look at my data, you'll notice the first 9 entries are not a number. And the reason for that, as we discussed on Monday, is that there aren't enough measurements to compute an average over 10 measurements. So it inserts not a number because it doesn't have enough. And that's just one of the pathologies for the rolling window average. So that being the case, when you transform your data through smoothing with rolling window average, you have to decide what you want to do with these first K-1 measurements that are going to be not a number. Now, certainly some choices that you have, you can set it to 0 if you choose. You could also set it to the mean. And setting it to the mean has a special property in that it does not alter the central tendency, the sample mean. It does not alter the standard deviation. So that's one of the reasons why one might want to choose to substitute not a number entries with the mean. Okay. Any questions about this? Does that make sense? Okay. So now we go ahead and we do that. And just to verify, because it's nice to tinker with some of the behaviors, especially if you're using an API option that you don't use very much. Now, in this case, we go ahead and we create a new column in our data frame, roll X dash close. So it's the rolling average of a window X size for the closing price. And Pandas makes it, or data frame makes it very easy to do that. You just assign to a slice notation for a new column, and the slice text that you use will be set in the data frame as a new key value for the dictionaries in that data frame. So we create a new column, and this new column, we decide to replace not a number with the sample mean for that particular column. And so here we have the assignment, and then we go ahead and we call fillNA on the slice. And so when you slice a column, excuse me, from a data frame, you get back a series. And the series also has the same set of APIs or methods associated with all sorts of processes as the data frame does. And so here we call fillNA, fill in all of the not a number entries. And what we're going to fill it with inside this parenthesized expression is the sample mean for that column. And so we do all that, and we go ahead and we say, go ahead and show me what your result was. And so you notice here now, the first 9 entries of that particular column are 518.6 and change, right? Any questions about this? Does that make sense? And so if you were to verify various or calculate various summary statistics, you notice that the standard deviation doesn't change for the first version, ignoring the not a number entries when you substitute with the mean, nor does the sample mean change. Okay. So now that we've done this, first, any questions? Does that make sense? Okay. I'm looking down because the little control is there. Okay. Thank you. All right. So now, where was I? We're going to compute the UMA version. And for the UMA version, we're going to have a span of win size, which is 10. And so as we saw on the documentation, when you set a span, it's going to calculate alpha for you. Alpha is equal to, I think, I just forget already. I think it was 2 over the span plus 1. So it'll be 2 over 11, which is about 5.5, which is about 2 over 11, which is about 0.21, 0.22 or something like that. And so here we're going to compute the UMA version of our same closing price column, and we're going to store the UMA version in a new column in the data frame. So we go ahead, we compute that, and when we look at the head of that list, the first 10 elements, we'll notice that the first set of elements are not a number, right? They have actual values. And that's a function of UMA because it's a recurrence relation. And the 0th item is just set as your S value. And then the next item becomes your new measurement to which you apply that alpha that we talked about. Okay. Any questions about this? Yeah, no? All right. So now that we do this, what we're going to do is plot the 3 versions of our Costco graph. We're going to compute the unmodified closing price in blue. We're going to plot the rolling average version in red, and we're going to plot the UMA version in green. And so here, let's go ahead and do that. We'll notice, like we saw in the slides, the more high variability version, the wiggly version, is the blue, the unmodified. We have our red, which is the window average version in the red. And then the green is the UMA version. And so a consequence also you'll notice of doing that replacement fillNA with the mean is you'll notice for the first 9 measurements here in our red graph, we get exactly, I think it was 518 and change, which is why it's flat in the beginning. Any questions about this? All right, so let's experiment a little bit, and I really highly encourage you to experiment with all of this. We're going to override the window size, and we're going to redefine, we're going to set win size. Let me go up here and do it. We're going to set it to 20, right? Let's see what happens when the smoothing window is bigger. So let me rerun that cell. So I set the window size. And then when I compute the rolling average, I'm going to recompute it, all of this stuff, and recompute my average with the sample mean. You'll notice here, now, if I were to compute or show you the first 20 entries of my rolling window version, the first 19 entries are not a number, right? And so I replace them with zeros. And you notice the average is different, and it's no longer 518, it's 520, because it's the first, it's the sample mean replacing all those values for the 20th value through the last value, right? When you compute the mean, it doesn't include the not a number entries from the series. And so you'll notice this value that I've replaced, when I replace it with the mean, that mean is different because it's the mean of a different set of measurements. Does that make sense? Any questions? Okay. So now I do that, I change my window size, and now for my UMA, instead of using span, I'm going to df Costco. I'm going to use alpha, EW max close, and I'm going to set that to df Costco, the closing price, and EWM UMA alpha equals, say, 0.1. Okay. Mean. All right. So I'm going to, let me comment out the first version that used the span to calculate alpha. And now I'm going to change my UMA smoothing constant alpha. So that means 10% of the measurement is going to be determined by the new measurement, and 90% of the measurement is going to be determined by the history. And so if I do that, you'll notice when I compute or plot the first 10 values, you'll notice that every subsequent value, it doesn't change very much from the previous value. It doesn't react as quickly to the new value. Let me try my alpha equals 0.9. So that's the converse. You'll notice here, these values jump a little bit more rapidly because I'm counting the new measurement. And so here, let me set it back to 0.1. Let me save. And let me go ahead and let me plot the new versions. And so again, in the blue curve, I have the closing price, which is unmodified. In the red curve, I have the smooth version, and the smooth version has a window size of 20. So you'll notice the smooth version, it is almost curved and not jagged, right? It goes up, representing trends, but it doesn't really track well with the variability, excuse me, in the blue curve. The green curve, it responds more rapidly than the red curve does, but you'll notice here, for example, in this period where my cursor is, it drops faster than the red curve, but it doesn't drop that fast. So let's say we decided we're going to set alpha to 0.5. So we're going to say 50% of the new value is a new measurement, and the other 50% is the history. Let's see what that looks like. You notice here, the green curve, it follows very, very closely the action of the blue curve, right? But the red curve, it doesn't care, right? It's very, very smooth. It gives you the trends, kind of almost like a sine wave of the blue curve, but it's not as variable as the green curve is, which is the UMA. And so the impact of this alpha is how much the new measurement plays a role in the value of what's being reported. And that has a tendency, if your original closing price is very variable, it'll increase the standard deviation or instability in the resulting green curve. Okay, any questions about that? Does that make sense? All right. Okay, thank you. So now let's go ahead and let's bring in the Baltic Dry Goods Index. And for this Baltic Dry Goods Index, we're going to replace the default index with the date stamp. okay, and take a look at the first 10 elements. And again, we're going to compute the rolling average, okay? And because the rolling average uses this window, the first 19 entries here are going to be not a number. And so let me go back before I continue. I'm going to restore the Costco back to what it was before my explanation. Okay, let me do that. Save. Go back down. All right, let me do that. Okay, so we're going to read in Baltic Dry Goods Index, and we're going to compute the rolling window average with a window size of 20, which is what I changed it to. We're going to go ahead and do the fill not a number with the sample mean. And we see here the first 19 entries are the sample mean. I could show you the first 20, but I'm just showing, I think, the summary here. All right, so now I'm going to compute the UMA version, setting alpha using the span, as we discussed before. And now I'm going to plot the rolling window average, the unmodified, and the UMA version of the chart. Okay, so let's see, let's do that. And so here in the blue, we have the Baltic Dry Goods Index, okay? In the red, we have the window smoothed version of the Baltic Dry Goods Index. And then in the green, we have the UMA version. And like before, you see that the red curve is very smooth. And you can even see in prominent regions where the blue curve changes very rapidly. So right in this cursor region where I'm waving the mouse pointer, we see the blue curve drops dramatically and rises dramatically, but the red curve doesn't even track with it. The green curve in that same region, it drops a little bit and rises a little bit. And so again, the UMA version, because it includes or counts with specificity certain proportions of the new measurement based on the current measurement, it responds more quickly to rapid changes and is more representative if what's important to you is the recency of your measurements. And so here, again, we see our Baltic Dry Goods Index, and we see the impact of UMA. So depending on what's important to you, you have to choose a smoothing window if you're doing rolling window average, and you have to choose the alpha to be appropriate, depending on what you're after for the UMA version of your graph. Any questions? Does that make sense? Okay. Let me see if, okay. So let's continue on. Let me hide my meeting controls. And we're going to take a look at the correlation. Now, of course, when you call correlation, there's more than one type of correlation. We haven't gotten to the different types and why they're important just yet. We certainly will have a conversation about that. But here, the term, when you compute correlation between two temporal pieces of data, time series, it's often called a cross correlation. And so here I've defined a method, defined a function called cross correlation. And cross correlation is going to input two time series. One I'm calling data X, and the other I'm calling data Y. And so I have a third parameter called lag, and lag is going to shift the second time series some number of specified measurements into the future. And so here, excuse me, we call data X correlation, and we're computing the correlation between data X and data Y, but it's not just data Y, it's a shifted version of data Y. And so the shift method on the series will allow you to move that series in time, where time is measured in terms of the time steps. And so in the case of securities and the Baltic Dry Goods Index, each time step, excuse me, is a different day, or more correctly, a different reporting period. And so it'll move it one reporting period into the future if your lag is equal to 1, 2 if it's equal to 2, etc. And so it goes ahead and computes that shifted correlation. And the idea is to use your security, excuse me, as data X, and to use Baltic Dry Goods Index as your data Y series, and then compute the lag for the Baltic for lag of 0, lag of 1, lag of 2, etc. And when we get a maximum in that correlation, we know that that lag for Baltic most closely coincides with the value of that security. And that's how far in the future this leading indicator, Baltic Dry Goods Index, precedes that particular security. And this is from data. Okay. Any questions about this? Does that make sense? Yeah. All right. So we go ahead, and one of the things to pay attention to when you're defining functions in Python in the Jupyter Notebook, you can't have the function straddle two cells, right? The function has to be defined in one cell, because what will end up happening is that it will assume that it's brand new code. So for example, suppose, let me just go ahead and do this. I put my return statement here, and I'm going to comment out the original return statement. Let me save this. Now, when I call this function, it lets me do that. It thinks this return is just a free floating command, right? So it's really important when you define the block for your functions that this function be entirely contained, the block for it, within a single cell. Okay, all right. Any questions? No? All right. So let's go back and let's now define that function. And now we're going to define a series of lags that's between 0 and some maximum number of time steps. In this case, I think it was 81. And for that number of time steps, we're going to compute the correlation, and we're going to add that for each time step to our array cores. Okay, so we do that, and then we're going to go ahead and we're going to print out all those correlations. And you see for each of these lags between 0 and 80, I set that max time steps to 81. It's going to compute that correlation between the Costco share price, closing price, and the shifted version of the Baltic Dry Goods Index. So this is for a lag of 0. It's a lag of 1, 2, 3, etc. Okay. Any questions about this? Does that make sense? All right. And so now we go down, and here, once we know what the lag is, we want to find that particular lag associated with the maximum correlation. And that maximum correlation says that at this particular lag, Baltic Dry Goods Index is most tightly coupled with that particular time series, in our case, the Costco closing price. And so we go ahead and we iterate over our correlation array. And because correlation is in the closed interval between -1 and +1, you notice here in my condition, I check for the absolute value of correlation, because a maximum correlation can be negative or it can be positive, depending on what the correlation is between the two indicators. And so here we record the index associated with that maximum magnitude correlation, and then we go ahead and we report on it. Okay. So if I go ahead and I do that for this UMA smoothed version with those alpha parameters I've used of Baltic Dry Goods Index and Costco stock closing price, the maximum correlation was at a lag of 45, and the correlation was about 50.51. All right, so it's a positive, moderate correlation. Now, of course, there are some factors impacting this, because when you smooth data, we saw with the rolling window average, it represents each measurement with equal say within a potentially large window of measurements. It shows you trend information, but it throws away all of that detail. With the UMA version, we saw it's a little bit more responsive to the more recent measurements, but you have control over that recency, how much of your measurement is the new, how much of your value is the new measurement versus the history. And so that's going to impact your lag calculation, because it's going to change the shape and the variability and the recency of what you're reporting when you compute the smooth version. And so I'm going to change the window size, and you'll see when I change the window size that this lag is going to change. And it's going to change because the UMA alpha is going to change when I change my window size. So I'm going to scroll up, and I'm going to change my window size to 5. Okay. And so again, alpha, when we use span is equal to win size, alpha is equal to 2 over span plus 1. So it's going to be 2 over 6 or 1/3 or 0.33. And so I'm going to save this and we're going to replay everything we've done. And I'm going to go down to that lag calculation. Let me just go down a little more. Correlation. Okay. So now I'm going to find the maximum correlation. And we see now my correlation is 0.53. So it's increased and it's a lag of 56. So the leading indicator, that period for which it precedes the security is longer, right? So it's an increased leading indicator. And so the smoothing that you use is going to impact your lag measurement because you're changing the consideration for the values when you do smoothing. Okay. Any questions about this? Does that make sense? Yeah. All right. And so at the outset, we said that the Baltic Dry Goods Index, plus or minus, is about a 6-month leading indicator, depending on your data. Okay. So let's go ahead and we'll increase our max time steps. And we'll repeat this experiment using an increased span over which we're computing this lag. Okay, so we go ahead. Let me do that. And now we're computing this lag over a number of time steps from 0 to 180. Okay, so 180 reporting periods exceed certainly 6 months. And if we take a look at our correlation, now over that longer window of lags or set of lags, we see that the correlation now is negative 0.87, which is a fairly strong correlation between the Baltic Dry Goods Index. And this lag says 169 reporting periods is how BADI precedes the Costco closing price. And you can actually calculate how many months and days of lag time this is if you know what the first reporting period is, which you do because you have that date stamp, and you know what the 169th reporting period or index into the BADI array, you can actually use the time APIs to compute that difference using the algebra. So you create one date, you create another date, and you just do the subtraction, and Python will do the algebra for you. Okay. Any questions about this? Does that make sense? And back of the envelope, 169 reporting periods. If you figure 5 days per week, it's about 6 months. If you considered 7 days per week, it's about 5.2 or so, 5.3 months. And so when you do calculation, I encourage you to use the time APIs to do the calculation because this is based on the calendar and it takes into consideration what the weekends are as well. Okay. Any questions? No? All right. And so lastly, now, once you know what the lag is, you can go ahead and plot in this case, we're plotting the UMA version of the Costco closing price data. That's the blue curve. In the red, we're plotting the shifted version of the BADI data, UMA smoothed. And then in the black, the third plot, we're plotting the non-shifted UMA smooth version of the BADI data. And then lastly, in the green, we're computing what was that? Brain hiccup. I think this is the B2. It's the, what was this? This was the, yes, I'm sorry, brain hiccup. It was the rolling window average smoothed version of the BADI data in green. And so you'll notice the UMA version of the BADI data, non-shifted, looks a lot like the window rolling average smooth version of the UMA data non-shifted. So the black curve looks a lot like the green curve. And that's because of how we set our alpha. Alpha, in this case, the window size is equal to 5. So 2 over 5 plus 1 is 6. That's 0.33. So 33% of the value for the UMA smooth version is going to dictate what the value is at each time instant for a recurrence relation. And so part of the assignment for project 3 is to do a study, and that study is going to represent a period of time pre-COVID from January 1, 2020, during COVID, and it's up to you to decide what that during COVID is, that period of time, and post-COVID, I'll call that COVID recovery, after COVID was considered as over up to December 31st, 2022. And so for part of this, you'll be going off and looking up sources online about the timeline for COVID and determining what periods of time represent pre-COVID, COVID economic shutdown, and COVID economic recovery. And then you'll be looking at the relationship between different market sectors through various securities, what that relationship is, how the relationship changes during those phases of time, and then enterprising to answer questions about those relationships. Any questions about this? Does that make sense? Okay. And so for this, yes? Yeah.
The homework PDF said to just get all of the data from January 2020 to December 31st, 2022.
Yes.
Are we still doing that, or are we just taking the point times that we think?
You're taking the whole thing, because those 3 periods will span between January 1st, 2020 and December 31st, 2022. It's up to you to determine which of those periods of time is considered pre-COVID, considered economic shutdown during COVID, and considered COVID recovery. And so you'll be consulting timelines and breaking apart that data into those ranges of time. Does that make sense?
Yeah, okay.
So you scrape the data once, and then you can put it into a CSV and then chop it up to suit based on what you believe those 3 phases of time are. Any questions? Other questions? No other questions? Okay. I was sort of budgeting for more questions. So I talked about alpha. I talked about UMA, gave the examples. So if there are no questions, then I can just end now. So thank you for bearing with me. Thank you for your attendance. And I will see you all in person on Friday. Take care.
Thank you.
Thank
You're
you.
welcome.
Thank you, Professor.
Take care. You're welcome. All right. Take care. All right. I'll see you later.